Okay, in this second part of the lecture, we are going to see some examples. So, the first one, we have to compute the Fourier transform of this function f, which is 1 in this part of the real line. So, this part is the interval minus a and 0 otherwise. So we also saw this function in the lecture 6 with a equal to 1, and we compute the Fourier integral of this function. Now we are going to compute the Fourier transform of this function. So we have, this is the graph of our function. Here we have the points minus a, and the function takes the value 1 in the open interval minus a and 0 otherwise. Okay, so we use what we have, which is the definition of the Fourier transform of a function f, and it's exactly this guy here. We can use this notation or the other one with this weird f, capital F. Okay, so hat f of omega, which is the Fourier transform of f at omega, by definition is equal to this number here, 1 over square root of 2 pi, and this improper integral from minus infinity to infinity of f of x and this complex exponential function e to the power minus I omega x. And we integrate in x, and that's why we have here this omega, and when we integrate in x, this becomes independent of the variable x, and we only have the variable omega, and that's why our Fourier transform only depends on omega. Okay, so now we use the definition of f, that, if you remember, is 0 outside the interval minus a, and inside that interval is equal to 1. That's why this minus infinity turn into minus a, and f of x turns into 1. And well, we just copy this part because we don't have to do anything yet. Okay, so now we need to integrate this guy, this exponential, which has this antiderivative, but this formula is okay if the omega is not equal to 0. Okay, we will analyze that case equal to 0 shortly. So here we have an antiderivative for this function, so we solve this integral and we have to evaluate this at a and minus a, and that's what we have here, this quotient, this subtraction. And okay, this number, we put it together with the factor that we have in front. So here is our minus, and here we have I and omega. Okay, so this can be rewritten in such a way. I don't know if you remember that these guys with some 2 or 2 times I are related, give us the cosine or the sine. I don't know if you maybe remember from the previous part of the lecture. So let's take a look at what we have here. This minus with this minus became here a plus. So then we can also see that this minus with this no, sorry. So this should be familiar in this lecture for you, in the sense that it's almost sine of some alpha that we are going to find out in a second. So we try to rewrite this as sine of alpha. So what we do from this line to this one is this minus here, we put it here, so we kind of distribute this minus, so now this would be positive and this would be negative, and that's why we have this guy here. And then, since we know this formula, that sine of alpha is equal to this quotient with complex exponential, we add these 2 times I in a smart way, let's say. We already have this I, so we have this I here, and now if we multiply by 2, but to keep the identity we have to divide by 2 also. So now what we get here in this blue circle is exactly sine of A omega, okay? Then our computation of the Fourier transform of f, for this f, which takes the value 1 in the interval minus a, and 0 outside, turns out to be this 2 over square root of 2 pi times this function sine of A omega divided by omega. We can also do some more step here, because 2 over square root of 2 gives the square root of 2. So finally what we have is this expression, but remember that to be able to integrate, we ask this omega to be different from 0. So now we wonder what's going on at omega equal to 0. So far we have this expression. For the Fourier transform of f, we have this expression when omega is not equal to 0. Okay, so we remember that we can use this hat notation of, or also equivalently this other notation with capital wir f. And okay, so we have that expression when omega is not 0. So what's going on at 0? We take the limit of this expression that we got for the Fourier transform when omega is not exactly 0, and we take the limit and see what happens. So remember that this is just the expression that we got, and here we have this problem that this guy goes to 0 and this guy goes to 0. So if you remember, we have a tool to solve this limit in this situation. We can, well, first of all, we can put this number out of the limit because it's just a number, that's why it's here. And then for solving this limit, we can differentiate this function and differentiate this function and see if this auxiliary limit exists, which of course we are lucky and it exists. If we differentiate this, the derivative is just a times cosine of a of omega, and this cosine of a of omega when omega goes to 0 goes to 1. So the whole limit goes to a. So this is our expression of, this is the result of the limit of the Fourier transform of f when omega goes to 0. So we define this as the Fourier transform of f at 0. Okay. On the other hand, we also saw that the Fourier transform of f at 0 is exactly just by the definition and applying, we have the definition of the Fourier transform, and then we can set omega equal to 0. So the exponential that we have in the definition here turns out to be a 1. So we have this identity. And if we compute this, replacing the f for our actual function f, which is again this minus infinity and infinity disappear and become this minus a, and the function takes the value 1 there. So this integral is 2 times a, well, here is the computation, but the result is 2 times a, and we have this factor in the front, and again we recover this value. So no matter which way we compute the value of the Fourier transport of f, we got exactly the same value. And now we can write this formula that we have here for any omega in R, where remember that when we this expression in principle is not well defined when omega is equal to 0, because we have this omega in like dividing the sign of a omega. But when we write this expression and we think about all the omegas in R, we think that we are taking the limit of omega going to 0 when we want to take the value of this Fourier transform of f at 0. Okay? But we are allowed to write this formula. The only thing that you have to check is that the limit exists. Okay. Second, it's not the second example, it's like the second part of this example. We can also express f as an inverse Fourier transform. So we will show how to do that. Again, remember that we have these two definitions in the lecture. In the first part, the definition of the Fourier transform of the function and the definition of the inverse Fourier transform of the function. So we just will use the definition. You can see the notes, but the definition is exactly this. If you want to write your function f as an inverse Fourier transform, you have to compute this, you have this factor in the front and the integral from minus infinity to infinity of this exponential that here has a plus and not a minus as the Fourier transform formula. And here you put this, this function that we just got. Okay, so replacing this Fourier transform of f, which is exactly this green expression, we have to compute this integral. So this number can go out from the integral, and also in the next step this number turns out to be 1 over pi. Okay, we can forget about the number, and then we need to work with this expression here that in principle we have no idea how to compute this, but the trick is to remember that this exponential, this complex exponential function is exactly equal to these guys here, is the cosine of omega x plus I sine omega x. So remembering this and distributing this sum here, we can rewrite this integral as the following two pieces, two integrals. So here we have the first one with the cosine here, and the second one with the sine here, and this I is just a number, that's why it can go out from the integral. So now we need to compute these guys. Okay, and now we can observe that this is equal to 0. Why? If we call g of omega this function here, turns out to be an odd function, and we are integrating between minus infinity and infinity, which is, remember, the limit of m going to infinity of the proper integrals between minus m and m of the functions that we have inside. And we have this property that if we have an odd function and we integrate it in an interval of the form minus m, then that integral is equal to 0. So let's see that this guy is an odd function. To see that, we compute g in minus omega. So we have minus omega here and minus omega here, minus omega here, and now remember that sine of whatever is an odd function, so this minus go out from the sign. That's why we have this here. And then if we check how many minus we have, is 1, 2, 3, oops, sorry, not the omega, just this minus. So just the sign rule says that we have only one minus here, and this expression is exactly g of omega. So indeed, we just proved that this function is odd. And this is exactly what I was saying before, like for odd functions, we know that these integrals are equal to 0 for every m, and that for the definition of this improper integral automatically implies that this the second integral in our expression is exactly 0. Okay, so going back to our computation, the second integral just died, and now we have that f of x is equal to 1 over pi, the integral from minus infinity to infinity of this function, cosine omega x sine a omega divided by omega. Okay, now remember that in lecture 6 we found the Fourier integral representation of this function, but with certain value of a, which was 1. So let's compare these two guys. Okay, so here I just copy what we got in the previous lecture, which was this Fourier integral representation for our function f, which is the same that we have here, but with a equal to 1. And then in principle, these two formulas do not look the same, but they are equal. So we are going to see that. So remember, this red triangle is this guy, which is the Fourier integral representation of our function f. And this, but with a equal to 1, is the Fourier transform of our function. Okay, let's compare these two guys. We denote h of omega, this function, cosine of omega x sine omega divided by omega. And we have that this function is even. And to see that, we just use the definition. So we compute h of minus omega, which is minus omega here, and minus here. And then we use, as usual, that cosine is even and sine is odd. So this minus disappears in some sense, and this minus goes out of the sign. And now if we cancel these two minus, we get exactly h of omega, and this is exactly the definition of being an even function. And so we have this h is an even function. So we also know that when h, for every h even function, if we integrate h between minus m and m, that this is equal to 2 times the integral from 0 to m of this h, because of the symmetry that we have. Okay, so using this property, and also, well, taking the limit of m going to infinity, what we get is that the integral from minus infinity to infinity of this h is exactly 2 times the integral from 0 to infinity of h of omega. Okay, so this was our star formula with red. I think this is h. And we just proved that we can rewrite this guy as 2 times this. So with the computation that we just did, we can replace this yellow bubble with this one. Okay, and here remember that we are taking a equal to 1, that's why here we don't have an a. Well, we have it, but it's equal to 1. Okay, and now you can see that this was the expression that we got in the previous lecture, which is f expressed as a Fourier integral representation, and this is the one that we got now, a couple of minutes ago, f expressed as an inverse Fourier transform. Okay, and these are equal. And this guy is the a of omega that we were working the previous lecture. Okay. Some remark about this example. Thanks to the definition of this f in the previous example, computing the Fourier transform of f was easy. I don't know what happened here, but let's continue. So the Fourier transform of f in omega is an improper integral. Okay. And the definition, we can recall the definition, which is here, is this factor, remember, and the integral from minus infinity to infinity of f and this complex exponential function here, differential x. So remember that our function was something where something was the number 1, but could be whatever. Let's say this square with the question mark in certain interval and 0 outside this interval. So then this improper integral turns out to be a proper one when we work with this type of functions. Okay, which is exactly what is written here. And that's why, let's say, the other example was an easy one. So now let's see an example where we are not that lucky and we have to work a little bit harder. Okay, again, we need to find the Fourier transform of this function, but now, okay, we have some intervals here, but they are not bounded like the previous one, minus a, because now our intervals are unbounded, like from 0 to infinity and from minus infinity to 0. Okay, this is our function, the exponential to the power minus x if x is positive and 0 if x is negative. And here we have the graph of f, just to have an idea. Remember, if someone asks us to compute the Fourier transform of certain function, we only have the definition, so that's what we do. We just copy the definition, and that's the first step. Then the second step is replacing the f that we have, that now it's true that we jump from this improper integral, but instead of jumping to a proper one, now we are still improper because our new integral replacing the information about f gives us the exponential here, real exponential, but this integral is still improper because it's from 0 to infinity. So we have to compute this integral, an antiderivative of this function. We can rewrite a little bit this expression just with a common factor of x, because x is here and x is here, so we just take it as a common factor. That's what we have here written. And now we look for an antiderivative of this function, which is this guy. And we use the same notation, like, oh, we have to evaluate in infinity and then evaluate at 0, but it's not true that we can evaluate in infinity. So what this notation means is that we have to take the limit of x going to infinity. So what we have here is not the, so this is a number, so we can put it here in the front. That's one thing first to do. And then what this notation means, again, is just the limit when omega goes to infinity. And sorry, I think it's x here. Let me correct this. This is x going to infinity, x going to infinity. Okay, so it's the limit of x going to infinity, and here is we have that x is equal to 0. So now everything is okay apart from this limit, because we have to still compute it, but here we get a 1, and that's what we have here. Okay, and now we need to compute this limit. The limit of x going to infinity of the exponential of to the power minus x times 1 plus I omega. Okay, to compute this limit, we first observe that we can take absolute value of this guy, the function. Of course, the absolute value is always greater or equal than 0. And here we have this identity that we can, again, like split this exponential. And this guy, we are lucky because has absolute value equal to 1. This is a complex number. And remember that the absolute value, when we are working with complex numbers, are the real part to the square of the real part plus the square of the imaginary part, and everything with the square root on the top. So what is written here? Okay. So since this is the real part and this is the imaginary part, what we get using the trigonometric, the well-known trigonometric identity is that this guy is equal to 1. So we are only talking about this piece. So finally, the bones that we get are these guys, like the function that we want to take limit when x goes to infinity is between 0, well, the absolute value of the function that we want to take limit is between 0 and this function, which is the exponential to the power minus x. And this guy, if you remember the graph, yeah, it's like that, right? So we go to 0 when x goes to infinity. So what's happening is that our function is between two functions that go to 0 when x goes to infinity, which means that our limit, the one that we wanted to compute, is 0. So going back, replacing this information about the limit in the Fourier transform of f, we get this value. This minus 1 with this minus 1 gives us a 1, and then we have this expression. Okay. So now if we want, I mean, here it's okay if you finish here, the exercise is okay because this is the Fourier transform of our function x. But just to write it in a bit in a nicer way, we can multiply and divide with this by this number 1 minus I omega, which is like the conjugate of this guy, which is like the same real part and minus the imaginary part. And then we have this other expression, this other way of writing the Fourier transform of our function f. And what will happen from this line to that one is just this computation. We make this computation here, and you make all the distributive properties, and you get this value. Okay. Then another remark. The Fourier transform of f, complex valued, even though so takes complex value even though the function f is real. So what we are trying to say here in this remark is we started with an f that was taking that takes real values, but once we Fourier transform it, then the expression of the Fourier transform of f doesn't have to take only real values. In this case, we find that the Fourier transform of f also takes complex values. So that's what the remark is trying to say. Okay, more about this example. Remember that we have these two situations where f is continuous and discontinuous. Okay, for this example, remember the graph, f is continuous everywhere apart from 0, x equal to 0. So we know that the Fourier transform will coincide with f in the points of the continuity and gives us the average of the right and left limit in the points of discontinuity, in this case 0. And this is what we have here. F of x, it's equal to its inverse Fourier transform for all x different from 0, and gives us the average when we are at 0. Which in this case, you can see that this average is exactly 1/2. If we compute this limit from this side, we get 0, and if we compute the limit of this side, we get a 1, so the average is 1/2. Okay. So, again, by definition, the inverse Fourier transform of f at x equal to 0 is given by this formula where we just replace the x equal to 0, which makes that this guy turns out to be a 1, and we get this expression. Okay, which, remember, this improper integral just means this limit of m going to infinity, and we just consider this proper integral from -m to m of our inverse Fourier transform f of f, which we found that is this guy here. So now we need to solve this integral, and one way is just to split this rest that we have here. So we have this first piece and this other piece here. Okay, so for the second piece, the second integral, we notice that this function is odd. You can do it as an exercise, but we have this square that will kill the minus. But we have this omega here that will keep the minus. So this is 0 from the property that we have an odd function, and we are integrating in the interval -m, m. And this guy is an even function, again, for this square here. So we have that this guy is the same as 2 times the integral from 0 to m of the same function, which is written here. And now, again, this function appears in the, I don't remember if in the first part of this lecture of the previous lecture, but we already know this integral is the inverse of the tangent function of omega, and we have to evaluate this in m and 0. And okay, for any m, we just have this number, but if we make this m go into infinity, this function goes to pi over 2. And that's what we have here. So the limit, once we solve this limit, is pi over 2 and this 2 that we have here multiplying. So at the end, what we get is this 1/2, which coincides with the average of the right and left limits, which we compute before. Okay, So, some conclusion. So far we know that given a function f of x, we can Fourier transform it to get this hat f of omega, and once we have this guy, we can anti-Fourier transform it, which we just call inverse Fourier transform it, to get back our f. Okay, is I have a function, I do something, and then I undo the something I just did. Okay, that's why our we use f to denote the process of Fourier transform. And then we have this other f, inverse of f, like f to the power -1, to denote that we are undoing this Fourier transform. Okay. So we know how to do that because we have these two definitions. Given a function f, I know the definition of the Fourier transform of my function, so I can get the Fourier transform. And then if you say like, oh look, this is the Fourier transform of some function, then I know how to undo the process to recover my original function, because we have the definition, and the only thing that we need is the definition, and then of course knowing how to compute the integrals that are involved. Okay, so far we know that. Coming soon, I don't know if you remember that we were talking in lecture 6 that we will use Fourier transforms to solve partial differential equations. And how will we do that? So the first step would be Fourier transform. Let's think this as a verb, Fourier transform the partial differential equation. Once we have the partial differential equation, what will happen is that we will find an easier problem, an easier equation to solve. So we will solve that easier equation, but that equation is in terms of the Fourier transform of the solution that we want to find. Okay, no problem. Then we anti-transform the solution to get the real function, the real solution. And that's why we are learning all this stuff about Fourier transform. And this way of, okay, we know how to Fourier transform and we know how to undo that. So now for finishing this lecture, we mentioned some properties that we will need in the next one. So with that goal in mind, we first need to learn how to operate with Fourier transform, and some of them are part of the exercises that you have to do on Thursdays. So, operational properties. We are lucky that this Fourier transform is linear, which means that each time we have two functions, f and g, and two numbers, a and b, the Fourier transform of this new function, which is the linear combination, any linear combination of f and g, is just the Fourier transform of f, the Fourier transform of g, and is the same linear combination but of these two functions. Okay, that's what being linear means. So this is quite important, and we will use this next lecture to solve partial differential equation. Okay, last property is how the Fourier transform behaves with derivative. So we are lucky that we differentiate one time our function f, and then we compute the Fourier transform of our derivative, and then we are lucky that we have this factor in the front, I omega, and then times the Fourier transform of our function f. And that happens if we differentiate one time. If we differentiate two times, we have this guy here, which is exactly I omega square. That's why we have this minus here. So we have two times this factor. And again, the Fourier transform of the function f. Okay, you can imagine if we differentiate 3 times, then we will have this factor to the power 3. If we differentiate 4 times, then we have this factor to the power 4. So what we have at the end is that the Fourier transform of the kth derivative of f would be I omega to the power k, so this factor, and then the Fourier transform of f. Okay, we are not going to prove these properties. I think one of them is part of the exercises, but then if you want, you can prove it. It's not hard to prove it. But these are the two main properties that we need to be able to solve partial differential equations in the next lecture. So what we saw here was the two main definitions of Fourier transform of a function and inverse Fourier transform of a function, which are key for solving the partial differential equations in next lecture, and these operational properties. So, operational properties and how the Fourier transform behaves with derivatives, these two last ingredients or tools, together with the two definitions, the two main definitions, the Fourier transform and the inverse Fourier transform, are the four main keys, like ingredients that we will use in the next lecture, with, of course, the goal of solving partial differential equations.